Okay, so welcome everyone to Guided Study Group Week 9 of Math 140. And so I hope everyone did well on the midterm 2 and now you're ready for the materials for the final exam. So for the final exam, it's mostly going to be on things like antiderivative and integral, basically the beginning of the materials of Math 141. And so today we're going to be working on section 3.9, 4.1, and 4.2. And so first of all, in 3.9, we're familiarized with the concept of antiderivative. So a function, capital F, is called an antiderivative of f on an interval I if you have f gram of x, or the derivative of f. The first derivative of f is the small f for all x in the interval I. Then we also have the theorem saying if you have big F is an antiderivative of f on an interval I, then the most general form of the antiderivative of small f on I is big Fx plus c. So basically you add c onto the f function. And so here is the table of anti-differentiation formulas. So for some of the particular like common functions, so things that I would highly recommend paying attention to is this part is the function of x to the n with n is different from -1, and the particular antiderivative is going to be x to the m plus 1 over n plus 1. Then we also have the antiderivative of the common functions, which is trig functions. So we have cosine x, antiderivative is sine x. So if you have sine x and you take derivative, so which means sine x, take the derivative is going to equal cosine x. And then when you have, antiderivative. And when you take derivative of negative cosine x, you're gonna have sine x. So, and then you have secant square and secant times tangent. But these two are not that familiar. So like you won't be doing a lot of exercise on these two functions in Math 140, but definitely you're gonna see them a lot in Math 141. Then we also have things like indefinite integral. So this is like an extra part that I kind of want to mention because you guys gonna see it a lot in 141 and maybe at the end of like 140, maybe in a few more lectures. But just want to clarify if any one of you heard about indefinite integral. So this is the symbol for integral. So it's like a small s. So like a Greek way to say s. And then you have fx dx. This is called the general antiderivative of small fx, which is what we say big fx plus c. So this just introduce you the notation. There's nothing really special about this part yet. Some problems that you might be asked in this sessions is you're going to be asked to find what's the function of f if you're given the first derivative and the value of fa. So basically when you're given f prime of x, and then you have to figure out what is big fx, and then so is whatever, and then you have the most general basically it's asking you if you find f here, it's basically asking you to find the general antiderivative of fx. So here instead of that, so you have f prime of x, then you use the table that we have earlier to find fx, and then the most general formula of the antiderivative is fx plus c, and then you're going to use this fa. When you plug in x equal a into this part, you're going to have it equal some value, and you're going to be able to find what is c. And we're going to see that in the example. Or you might be asked to draw the graph of f from the graph of big F from the graph of small f. And this is kind of like similar to what we did at the end of midterm 2, where maybe sometimes you're given the graph of f prime and you're asked to find some of the characteristic of f, like when is it increasing, when is it decreasing, you have a local maximum or local minimum over there, something like that. And so yeah, that's kind of like similar to what we did in the review last week. And 3, given the velocity acceleration functions and their values at one point and the initial value of position and velocity. Find what is the function of position and velocity. So the relationship here is kind of like the most common applications of antiderivative and also like derivative in that is in kinematics. So as we learn, I think in at the end of midterm 1 and at the beginning of midterm 2, the relationship between position, velocity, and acceleration is that the derivative of position is velocity, and the derivative of velocity is acceleration. And so when you take, so we have the antiderivative of acceleration is going to be velocity, and then the antiderivative of velocity is going to be position, which is also s. We're going to see that in the example. So the first one is question 41 of section 3.9. Find the function f given that the second derivative of f is cubic root of t minus cosine t, and you have two values of f0 and f1. So when you go from the second derivative to f, then you have to go through the middle step, which is the first derivative. So the first derivative is the antiderivative of second. So when you take antiderivative, you're gonna have f prime, and then when you take f prime of the antiderivative of f prime, you're gonna have f. So here, I'm gonna rewrite this to, so the second derivative, instead of writing this way, I'm gonna write t to the 1/3 minus cosine t. Now, we're gonna use the table that we have to find it. So the table that we have is, say, the antiderivative of x to the n dx is going to give me x to the n plus 1 divided by n plus 1. And so n here is, and n has to be different from -1. Here n is 1/3. So I'm going to put in, it's going to be t to the 4/3 divided by 4/3. Minus, so the antiderivative of cosine t is going to be sine t. So here I'm going to have the first, and then you have 3/4 t to the 4/3 minus sine t. And of course, you should add in c1 because that's the most general form of antiderivative. Now, continue from that, we're going to take antiderivative one more time. Here we have 3/4. We write it back as we see in that table where you have c multiplied like here. Here you have c multiplied fx. So antiderivative, that c is going to be keep constant, and you're just going to take the antiderivative of small f, which is going to be big F. Here we have again n is 4/3. So you're going to have x to the 7/3 divided by 7/3. Minus, so the antiderivative of sine t is going to be negative cosine t. Negative and the negative is plus cosine t. Then you plus. So c1 here, instead of writing this, you can write as t to the 0. Because t to the 0 is 1. Here we only have c1, which we can rewrite as c1 multiply 1, which is just t to the 0. And we can still apply this formula as long as the power is not -1. So here we're going to have, it's going to be c1t. And then you have to add c2 as well because that's the most general form. So when you go from the second derivative to the first derivative, you take antiderivative of that, you need to add c1. And then from f prime to f, you're going to have to add c2. And so here we have the most general form, but we have to find what is c1 and c2. Then we have to use these two numbers that we haven't used yet. So we have f0. When you plug in, oh, I'm going to rewrite this part so that it's come easier. 9/28 x to the 7/3 plus cosine t plus c1t plus c2. Now if you plug in t equals 0, you're going to have, oh, not x, sorry, it's the t. You're going to have 0 plus cosine of 0 is 1 plus 0 plus c2, and that one is equal to 2. So you're gonna have C2 equal to 1. Doing the same thing for the other number, so you have f of 1 is 2, which is going to give us 9/28 plus cosine of 1 plus C1 plus 1. And so doing that, you're gonna have C1 equal to 19/28 minus cosine 1. And so you find these two numbers, which gonna help you plug in this, and then finally you're gonna have f equal 9/28t to the 7th third plus cosine t plus 19/28 minus cosine 1 multiply t. Cosine 1 is a number. It's just not a very, like, full number or whole number that I don't want to put in a lot of decimals here. But if you want to represent it as decimal, that's completely fine. And then plus 1, that's C2. And that is my final answer for these questions. Again, when you watch this online and you have any questions with whatever step I'm doing, please feel free to email me and I'll get back to you guys as soon as possible. The next example you have is related to kinematics. So you have a stone is dropped from the upper observation deck of the CN Tower, 450 meters above the ground. So this one is 450 meters, and this is the ground. I'll rewrite that part. So this is the ground. Find the distance function. So a stone is dropped from there, and so when it's going down, we have the gravitational acceleration here, which is 9.8 meter per second square. We also have the initial velocity is v at t equals 0 is 0 because it's dropped and it's not like throwing down meter per second. So there's no initial velocity. You don't give it any initial speed. You just drop it. So it's gonna increase the speed from 0. And then you have s of 0. So the position at 0 is 450 meter above the ground. So this is gonna be your 0 mark. Or you can put it as negative 470, because if you put this one as 0 mark and this is the positive direction, then this one is going to be negative. This is going to be negative 450 because it go against the positive direction. But you know that it is 450 meters above the ground. Here you take the positive direction as going below. You can also take the positive direction as going above. Then s at 0 is going to be 450. But then your velocity as you going down is going to get more and more negative because it go against your positive direction. And also with the acceleration, your g right now is going to be negative 9.8 meters per second and not positive 9.8, because now the positive direction, if you take it as upward, then g is going to be against that direction. I'm going to take it as positive because it's just going to make my math easier algebra wise. But if you want to do it the other way, it's completely fine. You're going to get the same answer. So first one, find the distance velocity functions of the stone, the time it takes to reach the ground, and the velocity at the contact moment. Okay, first of all, it's a constant, it's a distance function. So you have, first, your acceleration is 9.8 meter per second. And so if you go from there to your velocity, then your velocity is going to be the antiderivative of a, which is a constant. And so if you have learned, if you look at some of the examples in the book, and I think Dr. Kasha kind of like went over 1 or 2 examples in her lecture notes, the antiderivative of a constant is, again, or you can write again as t to the 0 as the previous example. Then you're going to have is vt is going to be 9.8 t, because now it's going to be n plus 1 divided by n plus 1, which is also 1, and then plus c, plus c1. Then you're going to have v at 0 equal to 0 as given. So you're going to have 0 plus c1 is equal to 0. And then so you have c1 is going to be equal to 0. So your velocity function is 9.8 t meter per second. Then you have the position or the distance function, which is also the antiderivative of v, which is going to be 9.8 t squared divided by 2 plus c2. It's going to be 4.9 t squared plus c2. And again, s as 0 is given as negative 450 is equal to 0 plus c2. So your c2 is going to be negative 450 meter. Or your final function of the distance, final distance function is going to be 4.9 t squared plus or negative minus 450 meter. Now the time it takes to reach the ground, so the time it takes to go from the position of negative 450 to 0. So you're gonna set, you basically just gonna find t, so that s of t is equal to 0, or you set this entire thing to equal to 0. Therefore, you're gonna get t equal, I haven't done the calculation, but I would say it's equal to square root of 450 divided by 4.9 seconds. So if you have the calculator, feel free to type it out and find the actual decimal. And then from that value of t, you can plug it back in here of vt function to find what is the velocity at the contact moment, which is going to be 9.8 multiply that number. So it's going to be 9.8 multiply square root of 450 divided by 4.9. And it's going to give you some number using the calculators. And so the entire point of this exercise is that we have to know where should we start from, and always try to draw a diagram, because that's going to make you figure out things way easier. And especially when it comes to kinematics, always remember you have to choose a positive direction, because all of your calculations and direction of those, because it's not just mathematical, it's physical quantities. So it has a direction and it has to match with what we know in reality. So it has to match with kind of like, you know, gravitational principles. So the way that you choose a positive direction is very important, because it's going to design the sign of your quantities in your calculations. I think I did the calculations and it gave me like velocity equal to 63.91 or something. But yeah, feel free to like do it on type it out on your calculator if you need the actual number. Part B, if the stone is thrown downward with initial speed of 5, how long does it take to reach the ground? Okay, now the initial conditions just change. So your position at 0 is still 450 meters, but your velocity now is going down 0. That's the ball, not the 0. And so this is value of g is equal to 9.8. And I still choose this as a positive direction, and this is 0 where you have the ground. So, and now it's equal to 5 meter per second. So starting from, we'll use another color. Starting from this part is going to be different. And so here, you look at that, you have v at 0 is equal to 5, which is 9.8 multiply 0 plus c1. So c1 is 5. And so you have Vt is going to equal 9.8 T plus 5 meter per second. And now your function of St is also going to change, which is going to be 4.9 T squared plus 5T minus 450. Because if you do the same way, trying to find what is C2, and you put in as 0 as negative 450, you're going to get the same value of C2, because then these two is going to be 0 at that point, meter. Now, how long does it take to reach the ground? And so again, now you're going to solve for find T, so that you have S of T. At that point, at that time, it's going to give you 0, which is you're going to solve 4.9 T squared plus 5T minus 450. And so I think if you solve for this, give me a second. I need to pull up my notes, because I have the number there. I don't remember what exactly it is. Okay. We have antiderivative and you have that part. Okay, I don't have a number here, but yeah, just solve for what is the value of t here, and you're gonna get the number of seconds that it dropped from the ground. You can use what we learned about quadratic function to solve this part. I don't remember where I noted down, but yeah, that's just the general procedure. You can always do the math, and I don't want to go too deep into that. So again, if you have any questions, let me know. And even if you just want to check if your answer is right, also email me. I don't have a calculator right now, but when I see your email, I think I should be able to find a calculator. Next one is section 4.1, and then we have 4.2. So 4.1 and 4.2 is basically showing us the way to that we actually, like in the old time when we haven't had like the functions that we're going to use to solve antiderivative very quickly. This is the way that people usually do. And so the definition of an integral is the area of the region S that lie under the graph of a continuous function f. And so that is integral, but how to find it? In the old time, people write it as the limit of the sum of the areas of approximate rectangles. So basically, what they did is that if you have a function like this, you know the fact that integral is this area. But usually this is very odd function, and this is not like, you know, a trapezoid or a rectangle or like a triangle, things that are easy to find the area. So what they did is that they divide this into many small pieces of rectangle, and the smaller they divide them and they sum the area together, it gets closer and closer to the actual area under this curve. Because you can see here, like the difference is very small. It's just like the little part that we're missing. So this is the way that we write it. And so we say the integral, or that area under the curve, is the limit at ends approaching infinity. So as we say, as we divide it more and more rectangles, it gets closer and closer to the actual area under the curve of the series from I equal to 1 to n of these rectangles. So f of x1 here is basically f of x1, f of x2, and f2 f of xn. It's basically just the height of these rectangle. So this is, maybe say this one is x1, this is x2, this is to the xn. And so f is just the height, and then you have delta x. And as we divide them, make sure that these rectangles are equal to one another in the width. So delta x is just the width of the rectangle. And as we all know, the area of any rectangle is width multiplied length, which is also the height in this case. And so similarly, if you want to find what is the distance traveled and you have like the function or the graph of the velocity, you can also find the distance traveled by finding the area under that curve and using the limit method. Then we have section 4.2. It comes to the definition of definite integral. So the definite integral of function f from a to b is defined and denoted as this form. The integral from a to b, fx dx. And this one is equal to that limit of n approaching infinity, or kind of like the limit, the sum of all of the area under that curve. Given that that limit exists, and given the same value for all possible choice of sample points. So if you use like 4 sample points of 5 or even like 100, make sure that they're going close to like the value. Because if you like divided them into like 5 rectangles and then 6, or like just like 12, and to give you very different answer, then maybe that limit doesn't exist. Because as you know, like if the limit exists, it have to approach like a single value of number. Even though it never reached that, it has to approach just one value. And if you use different number of sample points and you find, you know, different values of the limit, it means that the limit doesn't exist, because it doesn't approach just one number, it approaches like 1,000 or bunch of numbers, and so by definition that limit doesn't exist. And if that limit exists, we say f is integrable on the interval from closed interval from a to b. We also have the theorem saying if f is continuous on that interval from a to b or has only finite number of jump discontinuities. Now this part, it's kind of like giving us a sense, like say if you have a graph like this, oh sorry, not that one. You have then you have this point, and then you have this point, or you have like here, and then you have like here. Then you know when you find the area under this curve, it's still like this, and it's not that much of a difference if you only have a jump discontinuities. Then your f is integrable on the interval from a to b, or you say that that integral exists. However, why is it only limited to jump discontinuities? If you learn in Math 141, you're gonna see the fact that if it has like infinite discontinuity, like here, then you don't know where these things gonna be blowing up and if it's gonna exist or not. And then at that time, we're gonna have another way to find that limit, but that's gonna go deep into integral, and it's gonna be the main, one of the main focus of your midterm 2 in Math 141. And so we're gonna talk back to that at that time. But here, only remember, if f is continuous on that interval or has only finite number of jump discontinuities, then f is integrable on that interval. If it's integrable, then you have this integral equal to that limit that we talked about earlier, where you have delta x is going to be b minus a divided by n, which is going to be the width. So basically, if you have like an interval from a to b, and you want to divide them into n part, each of them is going to have the width of b minus a divided by n. And then xi, each of the xi in this value of f is going to be a, which is here, plus I multiply delta x. And we're going to see that clearer in the examples. Later on, we have some properties of definite integrals. So yeah, if you want to, you know, take a note for yourself or like spend some more time on this one, please mute me when you watch it online and maybe like take some note. But for me, like these are a little bit obvious to me. But yeah, these are some of the properties of definite integral that you have to use to solve some of the problems. So some of the representative one is that the integral from a to b of fx dx can be rewrite as the integral from b to a, the negative of integral from b to a of fx dx. So you can, you know, flip the boundaries and add a negative in front of it. If you have an integral from a to a, or your b is equal to a here, then you have that integral from a to a of fx dx is just going to be 0, because that's going to be an area under the point, and it's very, very small to the, and it's approach 0. Then you have an integral from a to b of c dx. So just a constant, and you want to take integral of that. It's going to be c multiplied b minus a. And so if you have two functions, you can split them out into two integral. Or if you have a scalar multiple of a function and you want to take integral of that, take that c outside and you just multiply it with the integral of that function alone. And then if you have an integral from a to b, you can also split it into the integral from a to c plus the integral from c to b. Then we have comparison properties as well. This one is not that commonly used, but in some cases it can be extremely helpful, because say here for the first one, for the last one, sometimes you can find the integral as easily, or some like solve some of the inequality by just, you know, if you notice that your function is always bigger than or equal to some small m and smaller than or equal to some big M on that interval that is taking integral of, then you can conclude that your m b minus a is smaller than your integral is, and then smaller than the big M multiplied b minus a. So let's get started and see. We're working on example 3. It's question 30 of section 4.2. Express the integral as the limit of Riemann sum. Do not evaluate the limit. And so here we write as limit of n approaching infinity, the sum from I equal to 1, f of xi delta x. And here let's find what is delta x. Delta x is b minus a divided by n, which is 5 minus 2 divided by n, which is 3 over n. And then your x value, xi, is a plus I delta x, which is going to be 2 plus 3i over n. And so in this case, it's going to equal limit of n approaching infinity. I think actually, yeah, actually it's going from n I equal to 1. That's 1 is going to be f of xi. F here is going to be x squared plus 1 over x. It's going to give us 2 plus 3i over n square plus 1 over 2 plus 3i over n. And this one multiply delta x, which is 3 over n. And that is the limit of the Riemann sum. And I forgot to kind of like mention in the review, this is what we call a Riemann sum. So just kind of like make sure of the terminology so that in the exam or something, you understand what the question is asking for. And so it's pretty basic. Just follow what we have in this part earlier about what exactly is the Riemann sum and how to find xi and delta x. So the important part here is to identify your boundary and what is the function of f, which is just whatever in the integral except for dx. Now, example 4, we're going to go the other way around and do that. So the limit here, if you look at it, you're going to see the first thing coming to mind if after you did the previous example, 4 over n is going to be delta x. And so you're going to have b minus a over n. So you have b minus a is 4. And now you look at this part of the, I think I forgot I here and I here. And so if you look at these, you can replace it at limit of n approaching infinity from n to I equal to 1. This one is 1 minus xi square, 4 plus xi square multiplied delta x. So you have your function of fx is going to be 1 minus x squared divided by 4 plus x squared. And then your xi, which is a plus I delta x, which is going to be, it's here is given as 2 plus 4 over n. Therefore, you're going to 4i over n. You're going to have a is 2 and b is equal to a plus 4, which is going to give us b equal to 6. Therefore, your limit here is going to equal the integral from 2 to 6 fx, which is going to give us 1 plus x squared divided by 4 plus 1 minus x squared divided by 4 plus x squared dx. And so just doing the same thing as before, but doing the other directions around. And again, if you have any questions or feel really confused about what I'm saying, let me know. We'll have the last example of today, which is question 38 of the sections in the book. Evaluate the integral by interpreting it in terms of areas. And so first of all, I'm going to use one of the properties of definite integral. I'm going to split it into two functions. So you have the integral from -5 to 5x dx minus the integral from -5 to 5. Remember this dx here. Square root of 25 minus x squared dx. Now let's, in terms of area, so you have to draw the graph out and see what is the area. And so here, if you draw the graph of x, you're going to have its line go 45 degree going through the origin. And you're going to have this one is from -5 to 5. And this is the integral from that curve to the x-axis. So here you can see that the area here is going to be negative because it's below the x-axis, and the area here is positive. So let's go back to the area. The area 4.1. So the area that we're talking about is the lines on the graph of the continuous function, and it's going to 0. It's going to infinity. It's going to from that graph to the x-axis, and if that graph is below it, I think we have one of the property here that say that if you have the graph is above the 0, which is above the x-axis, then you're gonna have that integral is positive. But if you have it below, it means that it's negative. Here you have the graph here is negative, which is below, so it's going to be, and if you look here, it's above, so this part is negative and this part is positive. And if you actually draw the actual graph, then you're going to see the fact that these two areas are equal to one another in magnitude, but opposite in signs. Therefore, the area from -5 to 5 of x dx, they're going to cancel out one another because one is positive and one is negative, but their magnitude is equal, so this one is equal to 0. Now let's draw the second graph. If you doing the same thing, and in this case, I'll draw it separately to make that. Square root of 25 minus x squared, if you draw it out, it's going to be the half of the circle from -5 to 5. And because this is a square root, it's going to be above the x-axis. So this is x. And so to find this area, basically, we're just going to take half of the area of the, it's going to be half. Pi r squared, r here is 5, which is 5 squared, which is going to give us -25 pi over 2. And this is my final answer for what is the integral. So if you're interpreting it in terms of area, and so it's like the only method that we can do it now, because we haven't really learned too deep into integrals, which we're going to learn more in section 4.3 and also in Math 141. But here, this is like one of the very convenient way. And usually if you're asking to do integrals and by using areas, usually that's going to be the graph that you can draw out. And some of the things you already learned, like, you know, hyperbola, parabola, or circle, area, triangle, something like that. Then you're going to be able to, it's just your ability if you're going to be able to interpret the mathematical symbols into maybe, you know, geometry and graphical features. So that's like the last thing I have for today. Practice, as I say, always do all the suggested problems on Canvas. Especially this week, we don't do derivative anymore, and it's completely new concept. So I would highly recommend you guys try as many problems as possible so that you won't get too confused and, you know, having a hard time next week when we go further into integrals. With that in mind, thank you for listening to what I'm saying, and I hope to see you guys soon. Just to let you guys know, next week I don't think I'm gonna have a live sessions, so I'm gonna post my recordings online ahead of time because I'm gonna be away traveling. So I'm gonna record it and let you guys know the link, and you guys can just access it on my YouTube channel as usual. So have that in mind. I'll see you guys next week. Bye.